Asymmetric cryptography is where PKI really becomes powerful. Instead of one shared secret, we have a public key that can be shared widely and a private key that must stay protected. With that pair, we can both encrypt data confidentially and create digital signatures that others can trust. Symmetric cryptography is the workhorse for encrypting large volumes of data. It's extremely fast, but it has one big problem. Both sides must already share the same secret key, and distributing that key securely doesn't scale. Asymmetric cryptography flips that challenge. Public and private keys make key distribution easy and scalable, but the operations are comparatively slow and resource-intensive. Modern enterprise protocols like TLS and PKI combine the two, use asymmetric crypto to agree on a fresh symmetric session key, then use that fast key for all the actual data encryption. You can think of asymmetric crypto as a billboard and a vault. The public key is the billboard. You want it everywhere. Others use it to encrypt data for you or to verify that a signature really came from you. The private key is the vault, tightly guarded, ideally in an HSM. It decrypts data encrypted to your public key and creates signatures that anyone can verify with your public key, but not forge. A public key by itself is just a random-looking number. It can encrypt data and verify signatures, but nobody knows who it belongs to. PKI solves that by introducing a certificate authority, or CA. The CA validates the requester's identity according to your vetting policy, then signs a data structure that contains both the public key and that identity. The result is an X509 certificate, a cryptographic ID card that says this key belongs to this specific entity. When you think about protecting a private key, think in layers, not a single control. Start with strong hardware protection, HSMs or secure tokens that make key extraction physically difficult. Add tight logical controls, hardened OS configuration, least privilege access, strong authentication, and encryption of any key material at rest. Then manage the lifecycle, secure backups, tested recovery, monitoring, and clear procedures to revoke or rotate keys immediately if something looks wrong. RSA's core trick is simple. Take two very large prime numbers, multiply them, and publish the result. Going forward, multiplication is easy, but going backward, factoring that massive integer back into its two primes, is astronomically hard with current algorithms and computers. All of RSA's security rests on that asymmetry. In practice, enterprises use RSA key sizes from 2048 to 4096 bits. It's widely used in TLS, VPNs, and SMIME, but it's computationally heavy compared to newer options. Elliptic curve cryptography, or ECC, is the modern alternative to classic RSA. Instead of relying on factoring, its security comes from a different hard problem on elliptic curves. The big benefit is efficiency. You get RSA-level security with much smaller keys. That means faster operations, less bandwidth, and a better fit for mobile, IoT, and high-scale TLS environments. RSA and ECC deliver roughly the same security levels, but with very different costs. At today's parameters, a 256-bit ECC key buys you what a 3072-bit RSA key does. That translates into smaller certificates, faster handshakes, and lower CPU usage with ECC, which really matters at scale or on constrained devices. The trade-off is compatibility. RSA works almost everywhere, including legacy systems. ECC assumes reasonably modern clients and libraries, so migrations need to be planned carefully. Digital signatures exist to give you three powerful guarantees. First, integrity. If anyone changes even a single bit of the signed data, the signature check fails. Second, authenticity. The signature proves which private key holder produced it. And third, non-repudiation. Because only that signer controls the private key, they can't later credibly deny having signed it. A digital signature always starts from the data, but we almost never sign the data directly. First, the message is hashed with something like SHE256, producing a fixed-size digest. Then that digest is encrypted with the sender's private key. That encrypted blob is the signature. To verify it, the receiver hashes the message again and decrypts the signature with the sender's public key. If both digests match, the data is intact and the signer is authenticated. When two systems want to talk securely, the The hardest part is agreeing on a symmetric key without anyone else learning it. We can't just send that key over the wire. Instead, each side keeps a private value and only sends a related public value. Using some math, both sides combine their own private value with the other side's public value and independently arrive at the exact same shared secret. That secret then becomes a temporary AES session key for fast, encrypted communication. Diffie. Hellman in TLS is all about using short-lived keys. For each connection, the client and server run a DH or ECDAS exchange to create a fresh session key, then discard the DH private values. The long-term certificate key only signs the handshake. It never becomes the session key. That separation is what gives you forward secrecy. Even if an attacker later steals the server's private key, they still can't decrypt past sessions they recorded. You can think of a TLS handshake as a four-layer stack. First, identity. The server proves who it is by presenting an X509 certificate chained to a trusted CA. Second, authenticity. The client verifies the server's digital signature, typically with RSA or ECDSA. Third, key establishment. They run an ephemeral key exchange, usually ECDAE, to agree on a fresh shared secret. Finally, confidentiality. That secret becomes the symmetric key, opening an encrypted channel with AES for all application data. To wrap up, focus on the story, not the jargon. Everything begins with strong key pairs and protecting private keys like crown jewels. Choose algorithms that balance security, performance, and compatibility. Use signatures and key exchanges correctly. Then orchestrate these pieces, so TLS and your enterprise PKI work together as one coherent, resilient trust architecture.